This handwritten diagram maps out the complete architecture of an artificial neuron. It is the smallest, individual decision-making unit used in machine learning. Today, we will break down its anatomy, calculate its math by hand, and then write it in Python. Looking closely at the left side of the diagram, we start with the intake phase. The neuron receives multiple pieces of information, labeled here as X. Because not all information is equally important, the neuron multiplies each input by a specific weight, labeled W, which dictates how heavily that specific piece of data should influence the final decision. Moving to the center, the neuron collects all of those weighted inputs and adds them together inside this summation node. We also add a baseline value called the bias, or lowercase b, which shifts the total sum up or down to help the neuron trigger at the correct threshold. Finally, the right side of the diagram shows that raw sum passing through an activation function. This shapes the number into a clean, readable output. That sequence, intake, sum, and activate, is a complete artificial thought. This top red box outlines the concrete math behind that process, an operation engineers call the forward pass. The formula is z equals the inputs multiplied by the weights plus the bias. The second line breaks down the dot product. We take the first input, 0.3, and multiply it by its specific weight, 0.4010319. We repeat this pairwise multiplication for the second and third inputs, and then add those three products together. By adding our bias value to that total, we land on a final z value of exactly 0.922. However, this raw number is difficult for a computer to interpret as a clear decision. To make the number useful, we look at step 2. We pass our 0.922 value into a sigmoid activation function by plugging it into the negative exponent of the denominator. This mathematical operation squashes any raw number, no matter how large or small, into a clean range between 0 and 1. This interpretation box on the right translates the math. Our final output is 0.715. Because the sigmoid function bounds the number between 0 and 1, we read this as a probability. Common for probability, AI engineers use other mathematical traffic controllers like ReLU, TAN, or simple linear functions, depending on the specific outputs they require. Now we must address the problem of error. This green table shows our target data, the correct answers. If the neuron's forward pass predicts an output of 0.622, but the target table says the answer should be exactly 1, we have an error margin of 0.377. The neuron was wrong. To fix this, we look at step 2. By taking the derivative of our loss, we find the gradient. The gradient, calculated here as negative 0.08889, tells us exactly how much of the error was caused by our current weights. Step 3 shows the correction. To update weight 1, we take the old weight, 0.8, and subtract our learning rate multiplied by the gradient. This yields a slightly adjusted, more accurate new weight of 0.808889. Pause the video here. Using the same formula and the gradient we just calculated, find the precise new values for weight 2 and the bias. Here is the correct math. The new value for weight 2 is negative 0.391, and the new bias is 0.108. Taking these new values, recalculating the error, and updating them again over thousands of cycles is the mechanical definition of machine learning. This Python code executes our manual calculations. With NumPy, complex arithmetic requires few lines. The forward pass is isolated here. The exact dot product is mirrored by NP dot, processing inputs, weights, and adding bias. Finally, the terminal output perfectly matches our calculated 0.71555 probability. Zooming out, you can trace the entire path, from intake anatomy and dot product calculations to error correction and executable code. By linking millions of these single units into layers, engineers build the complex neural networks powering modern artificial intelligence.